Let's look at some more interesting instructions, in particular the instructions that move data around the processor. We'll begin with the simplest, which is the register to register move instruction, which is what you use when you have a value in one register and you want to move it to another register. So let's imagine that there's a value in register 8 and we want to move it into register 9. The instruction is called the RR move instruction because RR stands for register to register. The Q indicates that we're going to move a quad word. A quad word is 8 bytes, and the fundamental data type on the y86 processor is in fact 8 bytes, and so you'll see that many of the instructions end with a Q. So RR move Q, %R8, %R9 says I'd like to take the value that's in register R8 and move it into R9. If you've looked at the book, you'll see that they use a notation to describe precisely what an instruction does, and that notation looks like this. So you can think of it kind of like saying the register file is a big array, and the entry in the array that we want is the one that we're going to call RB. And what we'll do is we'll take register RA, we'll use that as RA is the number of the register, and so that's going to tell us which entry of the register file we want. And we'll take the value in that entry and we'll put it into the place in the register file referenced by RB. Now you might be asking, where does RA and RB come from? And that's when we need to look at the instruction encodings. So you'll notice that the RR move Q is a 2-byte instruction, which has an opcode and a function. For now, that function will always be 0, but we're going to come back to that a little bit later. And then it takes 2 registers, and we call those registers RA and RB in order in which they appear in the instruction. So when we have this particular RR move Q instruction, we see the opcode 2, the function 0, and then RA is register 8, and RB is register 9. So this is what the instruction looks like in memory in little endian representation. Now, if I want to give you the hex value for that, we're going to have to remember how to convert between little endian and hex notation. So the encoding for this instruction actually has 8920, which looks a little backwards. Why is that? Well, little endian says that the first byte that we see in memory is the low order byte. And when we write a number in hex, the low order is on the right, just like it is when we write in base 10. So we take the low order byte first, that goes at the end, then we take the next byte, and that goes before it. So we sort of have to swap when we write these things in hex. And you'll see that this happens in a number of different cases as we go through the rest of this video. Let's now look at how we put a constant in the register. Like, how do we get a value there to begin with? That's called an immediate instruction. Immediate refers to a constant value that we actually encode in the instruction. So in this case, the instruction is the IR move Q for immediate to register, and it's a move instruction. And again, it's a quad word. Now, its 2 arguments are the constant that I want to place in the register, and then the register I want to place it in. So precisely what's happening is we're taking val, which is a field from the instruction, and we're placing it into the register file, into the location referenced by the register in the RB position. So what does that mean? Well, that means that RB is going to take the destination register, in this case 9. And so you might say, well, what do we put for RA? And the answer is that whenever we don't need a register, we're going to use the value F, which is 15, because there is no 15th register on the y86. So this says there is no RA. Once again, we have to think about how this gets encoded in memory. So the constant that I want to move into the register is cafe, and we're going to represent that in a little endian format. Well, which are the least significant bits in this number? It's the FE. So that shows up first, then the CA. So once again, when I represent this in hex, this entire instruction, we start with the first byte, which is 30. That's the very least significant. Next, we get the F9, then we get the FE, and then we get the CA, and all the rest get filled with zeros. Again, you're going to have to practice this in coding, but eventually it will seem natural. Finally, let's look at how we move data to and from registers. We'll begin with the instruction that moves data from memory into a register. Typically, we call that a load because what we're doing is we're loading the register, and the place from which we load registers is memory. So let's look at the notation now because it's a little trickier. The place we're going to put the value is in the register file, and we're going to use the RA register to tell us where to put it in the register file. You might think that that's odd, but the reason is that the y86 always uses RB to calculate addresses when it's using memory. So processors have a number of different addressing modes, which is ways you can describe addresses in memory. Fortunately, the y86 only has one of those. So let's look at what that one mode is. It's called register plus offset. And what that means is that you're going to read a value out of a register, and you're going to add an offset to that value, and that will give you the location in memory that you're going to use to access the data. The way we represent that is that we say we're going to go to memory, that's the M, and we're going to go to it in an 8-byte quantity, which we call a quad word. And then the place in memory we're going to go is going to be some constant D, which is the offset that comes from the instruction here. We're going to add to that the value that we get when we read the register file at location RB. Let's look at an example. So here's a memory to register move queue instruction. The register that we'll use for addressing is RSP, which is register 4. So you'll notice in the instruction, RB is register 4. And I'm going to add the constant 4 to whatever RSP contains, and that will be my memory address. And then I'm going to place it into R9. So you'll see that RA is 9 and RB is 4. So for a moment, let's assume that the stack pointer contains the value hex 4000. Where in memory are we getting this data? Well, we're adding the 4000 to the constant 4, and we're getting the address 4004 in hex. And so we're taking the value that's in that location in memory and moving it into the register R9. Once again, we can represent this instruction with its hexadecimal encoding by taking the first byte, which is the least significant byte, placing it at the end, taking the next byte, the 94, taking the offset, and zero padding out to a full 10 bytes in this case. So that was how we move data from memory into a register called the load instruction. There's the opposite instruction, which is often called a store, which on the y86 we call the register to memory move. So we'll take a value in a register and we'll place it in memory. And we'll use the exact same addressing mode that we used before, that offset plus register. So this time, the place we're putting a value is this memory address. So it's the destination or the offset from the instruction added to the contents of register RB. And the thing we're going to place there is the value that we get out of the register file for the register RA. So once again, we'll use the same example. We're going to take the value that's in R9 and we're going to place it in memory at the location represented by 4 plus the stack pointer. Once again, we'll assume the stack pointer is 4000. So now what we're doing is we're taking the value that's in R9 and we're moving it into memory. And I'll leave it to you to now map the encoding back to this address laid out in memory.